Hi guys, welcome to the second video in our series looking at the atmosphere, and in today's video we're going to be looking at some of the factors that influence how much solar insolation actually makes it to the Earth's surface. Now in the previous video we were looking at a similar theme. We were looking at the global heat budget, and in that we looked at if we take 100% of all of the solar insolation that actually makes it to the outer edge of the Earth's atmosphere, how much of that actually makes it to the Earth's surface? And why isn't that value also 100%? What happens to the stuff that gets reflected or absorbed by the atmosphere? And in today's video, I say we'll be continuing with that, and we're going to be looking at some of the other things that have an influence here. So we've got four main factors that we're going to look at, and we did introduce these at the end of the last video, but we've got the oblique angle of insolation, we've got the distance of atmosphere, we've got the albedo effect, and we've got seasonality. Now to start with these oblique angle of insolation, now it's a kind of odd term, and it's just a really odd term, but it is about describing something that is relatively straightforward. So if we look at the diagram I've got here, we can see, a couple of things. One, the Earth is a sphere. That's fairly straightforward and obvious. As far as I know, none of you guys are flat earthers. But the Earth is a sphere. Now, because of that, the solar radiation, or the solar insolation, that makes its way to the Earth doesn't get evenly distributed across the whole planet's surface. When solar insolation hits the atmosphere, we get a set amount of insolation over any given area. And the problem that we have, if we look at the diagram here, this here, one kind of unit, if we want to look at it that way, of solar insolation, by the time it passes through the atmosphere and it makes it to the Earth's surface, it's only heating quite a small space. It's heating a relatively restricted area, and because of that, it heats it up very efficiently. If we go up towards the poles, and this is obviously the same in the southern hemisphere as much as it is in the northern hemisphere, that same unit of solar insolation, by the time it makes it to the Earth's surface, has to heat up a really large area. And that means it heats that area up much, much less efficiently. The way I think about this is if you've got a tiny room, a cupboard, and you're in it with with a candle for warmth. That candle might give off some heat that helps to keep you a little bit warm. If I take you, and I take that same candle, and I put you in the middle of a giant sports stadium, and I expect the same candle to heat up that space, it's not going to be able to. It's the same amount of heat, being given off, but it's trying to heat a much larger area, so it does it much, much less effectively. Now, the next bit we think about the literal distance of atmosphere that the energy, the solar insolation, has to travel through. Now, this is fairly straightforward. It's fairly common sense if you think about it. The more atmosphere you have to pass through, the more opportunity there is for energy to be reflected or to be absorbed by the atmosphere or by clouds. Thus, you get less getting through. Now this enhances the fact that the poles are colder than the equator. Because if we flip back to this diagram, you can see here that this one beam of solar insolation has got a much longer way to travel until it reaches the Earth's surface than the beam at the equator. And because of that limited amount of insolation that has to heat up a really big area, like we said earlier, is going to be even less efficient because that candle that I was talking about earlier, I've just cut in half because I've had to make it bounce off all the atmosphere, the dust, and the clouds that are in the atmosphere that it's had to travel through to get to that point. Now we've got another thing that comes into play here where we've got the albedo effect. Now the albedo effect is something some of you may have heard of, but the point with the albedo effect is that white things reflect energy. And what's a big naturally occurring white thing? A polar bear? No. Ice. Snow and ice reflects energy back very, very efficiently. And you think, where do we have lots of snow and ice? the poles. So at the poles, oblique angle of insolation means that one kind of unit of solar insolation has to heat a very large area. It also means that same unit has had to travel through even greater depth or distance of atmosphere. So lots of it has been reflected by the atmosphere and absorbed by it. And then to make it even more profound, that same unit, or what's left of it, now stands a really high chance of being reflected straight back off into space because the surface has got a lot more white on it, and that's a lot more prone to deflecting solar insolation. And I forgot I had this little statistic on this screen. But yeah, so in March and September, as much as 90% of solar insolation that makes its way through is reflected back off into space. And that is, really, really big deal. Now, obviously, the reverse of this is true in that dark colours, so browns and greens, are very good at absorbing heat, absorbing insolation. So if we think about the equator, where we've got lots of equatorial rainforests, they're very, very effective at absorbing the heat that gets there, and that heat is even more enhanced because it's heating up a smaller area, so it does it more efficiently, and it's got less depth of atmosphere to go through, so there's less of a chance of it being reflected or absorbed by the atmosphere. Now, the last one, and this is a really confusing diagram and there's a lot to it, so bear with me. Seasonality. Now, we are all aware that we have seasons. We feel winter more than any of the rest of them, but we know that we've got seasons. And what is important is where the sun is directly overhead changes dependent on the season. So, if we start at June 21st, so in June the 21st, the sun is directly overhead further north than the equator. And this is caused by the Earth's tilt on its axis. And because the Earth's tilted over, that means the northern hemisphere is getting more solar insolation than the southern hemisphere. Whoops. And this is also true in reverse. So if we look at the South Pole here, this is the southern hemisphere's winter. Now that means that, well, for one, the South Pole is now receiving no solar insolation whatsoever for the next 6 months at the actual pole, and as we go up, we're only getting a gradual amount more. We move through to September. Now in September, the sun's directly overhead at the equator, so it kind of balances out. We get to December 21st. We get to our winter. Now what I was just talking about in June 21st gets reversed, where we have got solar insolation much more prominent in the southern hemisphere, and the northern hemisphere is getting much less, so it's colder. We get through to March 21st, it's overhead at the equator again, and this whole process continues. And it alters on a day-by-day basis, because every single day the Earth moves on its, the Earth's orbit around the Sun continues, and the point where the Sun is directly overhead changes by the tiniest amount every day, and that changes the amount of solar insolation at any given latitude every single day. Now, and I gave the game away a little bit with this slide earlier, this is a nice kind of overall summary of what we've got here in terms of energy transfer. So I've already talked about how solar insolation, it's not transferred throughout the globe. Sorry, if solar insolation wasn't transferred throughout the globe, we would have really, really odd, uninhabitable, or inhospitable climatic conditions. The equator would be boiling hot, the poles would be freezing cold, and, mankind would be left with this little kind of band north and south of the equator to live on. Wouldn't be very big and it wouldn't be very comfortable. But we do get the atmosphere transferring heat from the equator to the poles, and you can see here in this graph, so we've got 0 degrees latitude, so the equator, big area of surplus. We have got huge amounts of net shortwave, so that's solar insolation, and not very much long wave energy being radiated back out of the Earth. And because of that, we've got surplus energy. We have excess. Now, we move either north or south of the equator, and the shortwave radiation that we get plummets. It drops very, very quickly. And that puts us into an area of deficit. So, like we were saying, the North and the South poles respectively are very, very cold. The equator is very, very warm. And thanks to atmospheric and oceanic circulation, we move energy from the equator to the poles, and it operates in reverse with the cold air that we have in these areas too, and that helps us actually have a whole planet where we can have human habitation spread throughout it. Now, that's going to wrap up today's video, guys. So, just to recap, in today's video, we looked at 4 of the main factors that influence the amount of solar insolation that we gain in any particular area. We looked at the oblique angle of insolation. We looked at the distance or depth of atmosphere that solar insolation has to travel through. We looked at the albedo effect, and we looked at seasonality. In the next video that we're going to look at how the atmosphere actually transfers energy from the equator to the poles, and we'll be doing that by looking at the 3-cell model. Until next time, I'll speak to you later, guys. Bye.